Welcome back. Now, remember in our last video, we looked at the Taylor series and we talked about the way in which we could generate or derive the Taylor series in its full form. In fact, we also went ahead to get the series as well as the value of the coefficients of each term within the series. Now, the coefficients of the terms in the Taylor series also share a very interesting relationship with the generalized Cauchy integral formula, and that is what we'll be laying emphasis on in today's class. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos. Now, remember that in our video on the higher derivatives of an analytic function, which we did earlier, if you have not looked at it, please make sure to check it out. We derived the generalized Cauchy integral formula as fn of z equals n factorial divided by 2 pi I integral over c of f of t divided by t minus z n plus 1 dt. Right, this is the formula we generated at the end of that video. Now, of course, we could rewrite this in terms of another point z0 so that we could make t our integral variable. We could make z our integral variable such that we would now have that fn of z0 to be equal to n factorial divided by 2 pi I integral over c f of z divided by z minus z0 n plus 1 dt. Now, do not forget, all of this at this point is just a change of variables. All of this is just a change of variables, nothing too serious. Now, we see immediately that if we were to divide by n factorial, we would have that fn of z0 divided by n factorial would be equal to 1 divided by 2 pi I integral over c of f of z divided by z minus z0 n plus 1 dz. Now, this is very interesting. Why? Because we will notice that on the right hand side, what we have here, this in fact was the value of the coefficient of the terms of the Taylor series, which we got at the end of our Taylor series video. What does that mean? It means that instead of writing the coefficients in this form, we could also write it in this form. So let's now put that into focus, right? Remember that from the Taylor series, which we generated in the last video, we already said that if you have a Taylor series f of z, which is equal to summation n starting from 0 to infinity cn z minus z naught n, then in this case we could define cn as 1 over 2 pi I integral over c f of z naught, or f of z, sorry, in this case divided by z minus z naught n plus 1 dz, right? This is what we would have in this case. Now, if we utilize this concept as is, the most important thing that occurs or that will come out is the fact that we can see that based off this, there is a relationship between this as the value of the coefficient and this as the value of the coefficient, which means they are exactly the same thing. Now, if they are exactly the same thing, what does that immediately tell us? What that immediately tells us is that these two values can be used interchangeably without any issues, right? Now, if they are to be used interchangeably without any issues, what we will then have at the end of the day is that we can rewrite the function based off the left-hand side. So we have n starting from 0 to infinity fn of z0 divided by n factorial, then z minus z0 is the power of n. Now, this is actually a very important identity. How so? We realize that the modern day Taylor series, which we use in calculus, which of course drops down into the Taylor-Maclaurin series, utilizes the coefficients of the Taylor series based off this identity. So it was important to bring this into fore to show that what we have in the calculus definition of the Taylor series, which defines the coefficients in this form, still matches what we have in complex analysis where we define the coefficients in this form, and that is brought to togetherness because of the existence of the generalized Cauchy integral formula. So this is very, very important, and it was why we had to take a minute to also show this relationship, so that when you see your Taylor series written in calculus with the coefficients used in this form, you do not think that this is different from the Taylor series that we have written right now. They are still talking about the same. Now that we have looked at this, the next bit of business that we would have to worry about is to discuss the next phase, which is what now happens when we consider not just the positive parts of the series. What if we now want to consider the negative parts of the series? That now extends beyond the Taylor series into what we now know as the Laurent series. So in our next video, we will be considering the Laurent series, the definition, the statement of the Laurent series, as well as the proof of the Laurent series. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos.